Hi everyone, welcome to our project. Today our project, the goal of our project was to predict medical insurance charges using demographic and health-related features such as age, BMI, smoking status, region, and their number of children. In this video, I'll explain how I use different learning curves as well as cross-validation to diagnose model fit, why XGBoost emerged as the strongest base model, what I did to systematically improve the performance of the XGBoost model, as well as how I verified the final model, as well as well-fitted and generalized it properly. First, let's move on to the learning curve for the four first base model. The first learning curve for the first base model, which was linear regression. As we can see, while the training MSE and validation MSE did seem to get closer together, the fact that the training MSE and validation MSE crosses or diverge means that there is a potential for a lot of variance for this model. As compared to the decision tree, we can see that the curves have stabilized much better and they're moving much more better into a more trend slash direction. And we can see this as well for our random forest, as well as our XG boost model. Um, in terms of evaluating between decision tree random forest and XG boosting, we can see that in the XG boosting, the training MSE, the difference between the training MSE and validation MSE was much lower, as well as the two curves stabilized much better when the number of training samples increased. Through the learning curves, we were able to decide that XG boosting model was the best model based on our prediction. We can see that in the XG boosting model, there is the lowest validation error. The controlled gap between training and validation is much more narrower, and the curve stabilized much better as the data increased, which would suggest this model provides very low bias and a much more better controlled variance. In terms of improving the regressor, we did of I did a couple few things. First was target transformation, followed by feature engineering, hyperparameter tuning, and finally ensembling and stacking. The first changes was converting our target charges distribution into log and clipping it. And the reason was that the charges distribution was highly right skewed. To stabilize its variance, I modeled log charges instead of raw charges, clipped extreme high log values, such as 99% or 98% percentile, and this reduced the influence of outliers, improved homodystacity, and reduced cross-validated MSE. It also improved Kaggle performance. The predictions were then exponentiated back to the original scale to make it improve in stability and generalization. Furthermore, I also did some feature engineering, such as I added much more domain-rich information into the interaction features, such as BMI squared, age squared, the interaction between BMI and smoker, age and smoker, age and BMI, age and children, and finally children and smoker. These features allow the model to better capture nonlinear relationships and real-world interactions. Cross-validation MSE improved after adding these features without exploding the train validation gap, which indicates bias reduction without excessive variance increase. With the addition of these features, the Kaggle test set will also improve significantly. Next off is a hyperparameter search, or 150 random trials. I performed extensive parameter tuning on XGBoost, uh, such as on hypermeters such as N estimators, max depth, learning rate, subsample, call sample by tree, min child weight, regularization terms, and each configuration was evaluated upon a tenfold cross-validation on the clipped log target. From then, the top three parameter with the lowest CV MSE were then selected. This lowered the bias while controlling variance through regularization. To further improve upon this generalization, I built three model XGBoost ensemble. I trained the top three tuned XGBoost models and averaged their log predictions, weighted averaging, reduced variance, and improved Kaggle MSE. Out of fold stacking with Ridge, I also generated out of fold predictions for each base XGBoost model and trained a rich regression meta model on those predictions. This allowed the model to learn optimal weights instead of simple averaging. Finally, I use AutoGloon Tabular with engineered features, clip lock target bagging and stacking enabled, and AutoGloon built multi-layer weighted ensembles combining light GPM, XGBoost back models, higher level weighted ensembles, which produce the best validation performance overall. And AutoGloon was a step up from our previously models letting AutoGloon automatically test out different light GPM and XG boosting models for our data to identify the best potential model. In terms of how the model fit was assessed, um, learning curves cross-validation MSE using five-fold or tenfold, as well as out-of-fold diagnostics was used um, in addition with the external Kaggle MSE to ensure that the model truly fits. The final model is a stacked and backed autoclone ensembled trained on log transform charges. It has clipped upper tail as well as featured engineered interaction features. It is optionally blended with tuned XGBoost ensemble. And finally, I believe this model is well fitted because it has low bias as because it's a non-linear boosted tree. Domain-informed interactions are also considered, and a lot of feature engineering processes was used to craft the model. It also had controlled variance in through methods such as regularization, subsampling, bagging, stacking, and sampling, as well as a strong external performance, whereas the CV MSE aligned with the Kaggle MSE, and improvements generalized beyond just the training data, but also improvements were seen in the Kaggle MSE. In terms of metacognitively reflection, my workflow followed a structured progression. First was diagnose the bias and variance using learning curves and testing out with four simple models. From then, the best model, which is XGB boosting, was then identified using CV, reduce bias and via feature engineering and log transformation on top of that XGB model, and then reduce variance and then sampling and stacking through the 150 random trial runs to identify the best XGB boosting model, and then finally validate every improvement with CV and external test performances. Our modeling started out as four different simplistic base model, identifying the best model. From there, building on top of it, stacking and sampling with 100 different trial runs, and finally, auto-glue to make sure that we have the best model after running some automation. And through this whole process, we've been able to reduce our Kaggle MSE tests of around 27 million to 23.9 million to 23.1 million. That is all. Thank you very much.